Hi, this is Dan, and this is a video to help us get used to this new distribution called the Students T distribution. Um, and this is on Wolfram demonstrations. There's a animation here that shows us how this compares with the normal distribution. The Students T distribution was made up by this guy named Gossett, who worked for the Guinness Brewery, and he wanted to figure out a way to do quality control with smaller samples. So he actually came up with this distribution just by pulling numbers out of a hat and plotting out the mean and standard deviations. And he noticed that the distribution of those means looked nearly normal. And as he increased the sample size, it became more and more normal. So what we call that is degrees of freedom. Degrees of freedom is always sample size minus 1. And we don't call it Gossett's distribution because the Guinness Brewery said he could not let that trade secret out. Eventually, he encouraged them to let him do it, but he had to publish it under a different name and not associate it with that. And so it's called the Students T distribution instead of Gossett's distribution. But pretty much what it is as you can see, the T distribution is this blue one, and the Z is kind of this brownish one. And there is a little difference, and the less the sample size, the more difference there is. So watch this. As I crank up the degrees of freedom, you'll see the T density, the T distribution, look more and more like the normal. And this little animation just goes up to 25, and there's barely any difference. And I'll go ahead and hit the zoom level so you can see what difference there is here. It's not very discernible from that range, but as we zoom in, there's a slight difference here. In fact, as degrees of freedom gets closer to 30, there's really not much difference at all. So when sample size is over 30, it becomes looking a lot like Z. So I'm going to go ahead and crank the zoom level down again, and I'm going to show you that animation one more time here. So if we get this all the way down to like 2 degrees, so if this is a sample size of 3, so if I take a random sample of 3, what kind of distribution could I say it might fit under if I'm trying to make inferences to the population it came from? And we can use this distribution here, the T distribution. And as sample sizes go up, we get a new curve. This would be degrees of freedom is 4, sample size 5. So what we get is each one of these is what we call a family of curves. Each one is a new distribution. And so when we had the Z distribution, we had this table. We used the Z table, it's no big deal. But now we're going to use the T distribution. Let me show that to you. So the T distribution, this is the one I use, shows the degrees of freedom here on the left, and then it shows the t-scores associated with each percentage. So the easiest way for me to show you is to go to the bottom. And see, as sample size goes to infinity, these numbers should look familiar. These are the same things we did when we did with the z-table, like a 90% confidence interval, or 95%, or 99% confidence interval. Those are the numbers we've been using. So as you can see, as sample size gets bigger, the more normal the t-distribution becomes. But as we shrink the sample size, let's follow this 95%. So 1.96 is our normal like z multiplier for a 95% confidence interval. If we go up the scale here, you can see these numbers get bigger and bigger. So the smaller the sample, the more variation or spread we see in that t-distribution, is what we saw in that animation. So instead of using 1.96, let's say we had a sample size of 10, which is 9 degrees of freedom, there we go. We would use 2.262 as our t multiplier. And if we go to our formula sheet, if we're going to do confidence intervals, here's our z multipliers. But now if we have small sample sizes or unknown parameters, unknown standard deviations, we can start using this estimation for confidence intervals right here for the true population mean. Notice here we use z if we have known parameters or large sample sizes, and now we just use t. Instead of 1.96, we'd use that 2.22 or whatever that number ends up becoming. And instead of using the population standard deviation, we can use the sample standard deviation. So these are the new formulas we're working with now. Honestly, in the real world, they're going to use t all the time because we almost never know the population standard deviation. But there's a few sections in your homework that will use known parameters, so you'll use z and the normal population standard deviation. But if you don't know those things, you're going to use t, and S, the sample standard deviation. And then for hypothesis testing, we're going to use the t calculation here. It's almost identical to what we did even when we were doing central limit theorem. Again, if we have unknown parameters, we can still use the t distribution. So if we say we do a t-test and we calculate it to be, let's say, 2. Well, let's go back here. Let's say we get 2 and there was 8 degrees of freedom. So here's 8 degrees of freedom. We've got a t statistic of 2. Well, where is 2? Well, this is a little different. Remember, each row is like its own family of curve. So we don't have all of the numbers like we did in the z-table. But if we look up 2, we know it's somewhere in between here. So if it's a hypothesis test that's two-tailed, we could say, you know what, there's about between a 5 and 10% chance of getting that much difference by random chance. If we were doing a one-tailed test, we would say it's between a 2.5 and 5% chance. So we can use this table to generally describe what's the probability of getting that by chance. The other way to do it is within StatCrunch. So you can look up the t statistic on here, see where it would, and figure out which interval it falls in. Obviously, like if we got a t-stat of 5, it would be way over here. Let's say if 8 degrees of freedom, so the probability would be less than 0.005, or if it's two-tailed, it's 0.001 or 0.01. If we use StatCrunch, we can go to Stat, and then we can go to Calculators. Just like we did the normal, we also have the t calculator. And then let's do the same thing. Let's say we have 8 degrees of freedom, and we have a t statistic of 2, and we want to go greater than 2. We want the area to the right, and there it is. So it's 0.04. So in the other one, we might say it's between 2.5 and 4%, but here with StatCrunch, we can get the exact percentage that is to the right. And if it's two-tailed, you would just double that to like 8% if it was two-tailed, because it could be greater than or less than. So we've got both the t calculator here, and in your homework you may have to use this to get more accurate, because on your t-table, for instance, if we have a sample size of 47 and we're supposed to use 46 degrees of freedom, well, 46 is even on here. So we go to our next best, which would be 45. If you need more accuracy, go to StatCrunch and use the t calculator. Hope this gives you a good start on how to use the t-table. Understanding that these numbers here in the body are like what we did z-scores. These are called t-scores now. And the degrees of freedom is based on n-1 when we're talking about just one sample, which is what we're doing right now. And this, so each one of these rows is like its own distribution, kind of like we see in this animation. As degrees of freedom, we get its own curve. So the areas change just slightly. The less the sample size, the more spread out the data is, and more spread out, honestly, our t-scores are. The more distance we have to travel to get that same percentage. So if you want to do a 95% confidence interval in t, use the middle row. 99%, use this far row. 90% is right here. And so you can use these confidence levels, and then these would be your t multipliers for confidence intervals. And then if you're using hypothesis tests, obviously you can look up your t-scores in here and figure out where do they fall within these probabilities. Hope this helps, and be sure to check out the other videos that we have over chapters 7 through 9.